Welcome to the deep dive. We've got a pretty interesting stack of source material here today. It's all about something called Grevm 2.0.
That's right. Specifically, we're looking at the design docs, the performance numbers, the real kind of nitty-gritty stuff.
And Grevm is, yeah, well, it's the engine, right, for running smart contracts, transactions on some of these blockchain systems.
Exactly. And the big goal for this version 2.0 is just speed. How to make things go much, much faster.
Right. So our mission for this deep dive is to really unpack how Grevm 2.0 is trying to achieve this huge speed up, mostly through parallelism and, what's actually new here, what makes it different, maybe better.
Think of this as like your shortcut through all these technical papers. We're pulling out the key ideas, the clever engineering, and importantly, the actual results.
Okay, let's dive in then. So the basic problem Grevm 2.0 wants to solve is pretty fundamental. Make transaction execution faster.
Yeah, much faster than just doing them one after another sequentially.
And the obvious thought is, well, parallelism. Just do lots of things at once.
Yeah.
If you've got 1,000 transactions, why not try and run, 100 simultaneously?
That's the intuition. But this is where it gets tricky, especially with blockchain stuff. Transactions aren't always independent.
Ah, dependencies.
Exactly. You might have one transaction where Alice sends tokens to Bob, and the very next one is Bob using those exact tokens for something else, maybe a swap on an exchange.
So the second one absolutely depends on the first one finishing correctly.
Precisely. And if you just, run them at the same time without managing that dependency or run them out of order.
You get conflicts,
Oh,
chaos,
hey.
wrong results.
Right. The system might read old data, the final state is wrong, and then you have this whole process of detecting the error, throwing away the work you did.
And rerunning it.
Yeah.
Which completely defeats the purpose of going parallel in the first place if you're just redoing everything.
Exactly. So that's the core engineering puzzle.
Yeah.
How do you manage all these potential dependencies to get the maximum parallelism, but also guarantee correctness? Make sure the end result is identical to running them one by one.
Which brings us to Grevm 2.0's specific approach. The sources call it a high-performance parallel EVM runtime.
Yeah, and it builds on this idea of optimistic parallel execution. That's not entirely new. Systems like Block-STM use it.
Optimistic, meaning just assume it's okay to run things in parallel.
Sort of, yeah. The basic idea is don't waste time figuring out all dependencies beforehand. Just go for it. Execute transactions concurrently, optimistically. Then, after they've run, check if any conflicts actually happen.
And if they did?
You abort the conflicting ones and re-execute them. It's faster if conflicts are rare.
Okay, so optimism is the base. But Grevm 2.0 adds some significant layers on top, according to these documents. You talk about task groups and this data dependency directed as cyclic graph, or DAH.
Right, the DD. Think of it as a map that's being built dynamically as transactions are processed. It shows the potential dependencies.
How does it know?
Well, it starts with hints, basically, educated guesses about what data each transaction might read or write. These hints might come from simulating the transaction quickly or looking at past patterns.
Okay.
So each transaction is a point, a node on this graph. And if transaction B looks like it needs data that transaction A writes, you draw an arrow, an edge from A to B. It's acyclic because dependencies only flow forward. B can depend on A, but A can't depend on B if B comes later.
Got it. Dependencies flow one way. But task groups.
Yeah.
That sounds like the opposite of parallel. Grouping things together.
Ah, but it's clever. This is where Grevm 2.0 tries to be smarter than pure optimism. The system looks at that DD, and if it sees, say, transaction 2 and transaction 3 have a really strong immediate dependency.
Like Bob using the tokens Alice just sent him in transaction 2.
Exactly that kind of thing. Instead of just throwing T by 3 into the parallel pool where it's almost guaranteed to clash with TX2 and need re-execution.
They group them.
Yes, they put them into a task group, and that whole group runs sequentially, one after the other, but within a single execution thread.
Okay, so you're sacrificing parallelism for that specific pair.
To avoid the near certainty of a conflict in re-execution, which would be even slower and waste CPU, it minimizes those aborts, cuts down on scheduling noise, and actually uses the CPU more efficiently for those tightly dependent chains. It's like saying, okay, optimism isn't going to work well here. Let's just do this a bit sequentially.
So the scheduler isn't just running things 1, 2, 3, 4, or randomly throwing everything at the wall. It uses the DAG, uses the task groups.
And it dynamically decides what to run next. It looks for transactions or entire task groups that have the lowest original index number but have no current dependencies waiting. Nothing earlier in the DAG needs to finish first.
Meaning it can jump ahead and run, say, transaction 10, if it's totally independent, even if transaction 3 is still waiting.
Exactly. Or it can run a task group containing transactions 4 and 5 as soon as transaction 3 is done, if that's the dependency. It makes the execution order much more flexible and efficient.
Okay, that's the core strategy. The sources also mentioned some clever implementation details. Selective dependency DAG update was one.
Yeah, this is about managing the complexity of that DAG itself. If you added a dependency edge every single time a transaction might have read something unexpected based on the initial hints.
The graph could get huge and slow things down.
Right. So Grevm 2.0 is smart about it. When a transaction finishes, it figures out what it actually depended on, and it only adds the most critical dependency edge back to the DAG specifically, the link to the highest index transaction it truly needed data from. Keeps the DAG lean.
Smart. Okay, adding edges selectively. What about removing them? They talk about a hybrid strategy for removing dependencies.
Right, because once a dependency is met, say, transaction A finishes and commits its changes, the edge from A to B in the DAG isn't needed anymore. Removing it tells the scheduler B it might be ready to run.
But when you remove it matters.
Hugely. Remove it instantly after A executes. That's fast for scheduling B. But what if A's execution had a subtle conflict only caught later in validation? You might have wrongly scheduled B.
And if you wait until A is absolutely fully confirmed and final.
That's the safest. No risk of re-executing B because of A. But it means dependency edges stick around longer, potentially delaying B's scheduling unnecessarily.
So Grevm 2.0 splits the difference, the hybrid approach.
Exactly. It looks at how the dependency was known. If it was inferred from those initial hints and execution seemed okay, the dependency edge is removed quickly after execution finishes. Speeds things up when hints are good.
Okay.
But if a dependency was found dynamically during execution or validation, meaning the hints were wrong or incomplete, a real potential conflict. That dependency edge is only removed after the first transaction A in our example, reaches finality, complete confirmation.
That makes sense. It balances speed based on likely good hints with correctness when things get complicated.
It's a really neat trade-off.
Another big thing mentioned was parallel state storage. What's that about?
This tackles a bottleneck that happens after execution. Even if you execute transactions in parallel, you often have this final sequential step where you gather all the state changes, like account balance updates, and commit them to the final block state.
And that commit step takes time.
Yeah, the docs estimate it can add like 30 to 60 milliseconds of sequential latency right at the end, which kind of eats into your parallel gains.
So parallel state storage tries to hide that latency.
Precisely. It's an asynchronous mechanism. While transactions are still executing and validating, this system is already working in the background, continuously building that final state representation. It overlaps the commit work with the execution work.
So by the time execution is done, the final state is mostly ready.
Pretty much, yeah. It dramatically reduces that perceived end-to-end time.
What about tricky things like minor rewards getting paid out or that self-destruct command? Those need the very latest state, right?
Good question. The parallel state layer handles this. It provides the necessary database interfaces so that if a transaction needs the absolute current balance of the miner's account or the status of an account being destroyed,
You can just read it directly from this parallel state layer.
yes, without needing to wait for some slow final sequential commit, it uses internal versioning to make sure the transaction reads the correct state valid for its point in time, even as the final state is still being assembled.
Okay, the design sounds really thought through, lots of clever ideas there, but does it actually work? Let's talk benchmarks.
Right, the results section. This is where we see if the design choices actually, pay off. They used a specific AWS instance, laid out the software versions.
Sure.
Pretty standard benchmark setup.
And the test was called Gigas.
Yeah, basically running mock blocks that use a total of 1 giga's worth of computation. They tested different mixes, simple transfers, ERC20 token stuff, more complex Uniswap v3 swaps, and importantly, they added some artificial database delay to make it more like the real world.
Okay, first up, conflict-free workloads. The easy mode, no dependencies.
Yeah, here you'd expect any parallel system to do well, and Grevm 2.0 does. It matches or even slightly beats Grevm 1.0 and Block-STM, especially on the complex Uniswap transactions. They hit something like 16.57 gigas per second throughput there.
Impressive. But you mentioned it was maybe a tiny bit slower on really simple transfers compared to Grevm 1.0.
And just slightly. That's likely the small overhead from the DAG scheduling logic, even when there are no dependencies to manage, but it's still well over 1 gigas per second, which is plenty fast for those simple cases, especially in a mixed workload.
Okay, baseline is strong. Now the interesting part, contention workloads. What happens when transactions do clash?
This is where they use that hot ratio concept. Simulate scenarios where maybe 10%, 20%, 30% transactions are all trying to access the same few accounts. Creates way more conflicts.
Like everyone trading the same hot token.
Exactly. They've focused on a hybrid test, a mix of transfers, ERC20, Uniswap with a 30% hot ratio, so reasonably high contention.
And the results.
This is where Grevm 2.0 really pulled ahead. Compared to Grevm 1.0, it achieved a 5.5x increase in throughput. Hit almost 3 gigas per second, 2.96 gigas in that contentious scenario.
Wow, 5.5x under pressure. That's significant. That suggests the DAG and task groups are really doing their job when things get messy.
It really does. It shows it's not just fast when things are easy. It handles the difficult cases much better.
Okay, but what about the absolute worst case? The non-parallelizable workload, like a perfect chain. A needs B, B needs C, C needs D.
The nightmare scenario, where theoretically you can't parallelize at all. They tested this explicitly.
How did Grevm 2.0 hold up compared to, say, Block-STM in that torture test?
Remarkably well, actually. Grevm 2.0 only saw a small dip in performance compared to just running it sequentially, like 5% slower for ERC20 chains, 3% for Uniswap chains.
Okay, so it recognized it couldn't parallelize and basically ran sequentially with minimal overhead. What about Block-STM?
Block-STM took a much bigger hit, around a 30% slowdown compared to sequential in those same scenarios. It was still trying and failing to parallelize.
30% slower than sequential is. Not great when parallelization is impossible anyway.
No. But the truly mind-blowing number here wasn't the throughput. It was the CPU usage.
Ah, right. How much work the computer was doing.
Exactly. In that worst-case ERC20 chain, Grevm 2.0 used about 128% of a single CPU core's capacity. So basically one core plus a tiny bit. Block-STM. Almost 3,000% CPU usage.
3,000%. So like 30 cores spinning like mad?
Pretty much. Thrashing,
Yeah.
trying to execute, detecting conflicts, aborting, re-executing over and over. For Uniswap chains, it was similar. Grevm 2.0 around 115%, Block-STM over 2,700%. That's a 95% reduction in CPU usage for Grevm 2.0 in the worst case.
95% less CPU burn. That's incredible. It means Grevm 2.0 isn't just slightly faster, it's vastly more efficient when faced with inherently sequential tasks. It doesn't waste resources trying to do the impossible.
That's the key takeaway. Those task groups and the DAG scheduler seem incredibly effective at identifying and handling non-parallelizable work efficiently, avoiding that massive overhead of pointless optimistic attempts and re-executions.
Okay, benchmarks strongly support the design. What did the analysis in the sources say about why this works so well? Any deeper insights?
One really interesting point was about optimistic parallelism itself. The analysis suggests it's actually more effective than you might guess, even with dependencies. They looked at dependency distance.
How far apart dependent transactions are in the block?
Yeah. If transaction 1 writes data that transaction 10 reads, the distance is 9. If transaction 2 reads from transaction 1, the distance is 1.
And longer distances are better?
Much better. The analysis showed that once the dependency distance gets to about 4 or more, the actual chance of a conflict drops dramatically. Many dependencies are spread out like this.
So pure optimism works quite well for those spaced out dependencies.
Exactly. And Grevm 2.0 leverages this. It uses the more conservative task groups only for those short distance dependencies, like distance 3 or less, the sources noted, where conflicts are super likely.
And for everything else, with longer distances.
It lets the optimistic engine run, maximizing parallelism where it's likely to succeed without high conflict rates. It's a targeted approach.
Smart. What about challenges or bottlenecks? The analysis brought up validation scheduling.
Right. This seems to be a key area for improvement. Validation, the final check for correctness, has to happen in the original transaction order, 1, 2, 3.
But Grevm 2.0 executes out of order using the date.
Exactly. So the validation step can get stalled. Even if, say, transaction 5 finished executing way early, it might have to sit and wait for transactions 1, 2, 3, and 4 to finish their execution and pass validation before transaction 5 can be validated.
Creates a potential queue or bottleneck right at the validation stage.
Potentially, yes. The sources contrast this with an optimization Block-STM has that can help speed up validation after conflicts, something Grevm 2.0 doesn't currently seem to use.
And getting things validated quickly is important, right? Because finality depends on it. And things like Removing those dynamic dependencies or using parallel state storage rely on finality.
Correct. So optimizing that sequential validation phase is pretty critical for overall performance. And its efficiency ties back to how good those initial hints were at predicting dependencies and avoiding conflicts in the first place. Fewer conflicts means smoother validation.
Okay, so looking ahead, where does Grevm go next based on these findings?
Well, they identified improving the dependency DAG management itself, looking at things like lock-free data structures to maybe reduce overhead when many threads access the DAG.
Makes sense. And tackling that validation bottleneck directly.
Absolutely. Developing faster validation algorithms, maybe borrowing ideas from other systems like Block-STM, using really high-performance data structures there.
And also just getting better at predicting dependencies up front.
Yeah, refining those hints. They mentioned doing more analysis on real-world blockchain data to understand how accurate hints usually are and how to best balance relying on them versus discovering dependencies dynamically.
Okay, so let's try and wrap this up, this deep dive into Grevm 2.0. What's the big picture?
I think it shows a really impressive evolution in tackling blockchain scaling. They've cleverly combined known techniques like optimistic execution with their own novel ideas, the DEX scheduling, the task groups, the parallel state storage.
And the results seem to back it up, especially under pressure. That 5.5x gain in contention is notable, and the 95% CPU efficiency win in the worst case is just massive.
It really is. It also gives us good insights into how parallelism works in this context, like the importance of dependency distance, and shines a light on the next set of challenges, like optimizing validation.
The direction seems clear. Building faster, yes, but also smarter parallel EVM engines. It's not just about brute force parallelism.
Agreed. It's about intelligent parallel execution, adapting the strategy based on the actual dependencies you find.
All right, here's a final thought then, something for you, the listener, to mull over based on all this. Grevm 2.0 makes these very specific trade-offs, right? It uses task groups for tight dependencies, distance equal 3, optimism for others. It trusts hints for speed, but waits for finality for dynamic dependencies. We saw huge efficiency gains, but also potential validation bottlenecks. So considering all the balance between optimism and conservatism, hint accuracy versus dynamic discovery, execution speed versus validation speed, what do you think is the single most critical factor going forward for building parallel execution environments that are not just fast, but truly robust and efficient for complex, decentralized applications? Is getting those hints perfect, making validation instantaneous? Something else?
That's our deep dive for today.